There is a moon in our solar system that has oceans, it has rivers, it has rain that falls from clouds, carves channels through the landscape, and flows into vast seas that stretch for hundreds of kilometers. It has a thick atmosphere, a weather cycle, and a surface shaped by the same forces that shaped Earth. And almost none of it is anything a living thing could touch without dying instantly. The oceans are not water. The rain is not rain in any sense we would recognize. The rivers do not carry anything that flows through our world. This moon is a place of liquid methane seas, ethane storms, and temperatures cold enough to freeze nitrogen solid. A world that looks, from a distance, almost familiar, and up close is one of the most alien places in the known solar system. This is Titan, Saturn's largest moon, and it may be the strangest world we have ever found. From a distance, Titan does not look dangerous. It looks beautiful. Wrapped in a thick layered atmosphere of deep amber and orange, it resembles nothing so much as a soft glowing ember suspended in the darkness beside Saturn's rings. The haze is real. A dense photochemical smog produced by sunlight reacting with nitrogen and methane high in the atmosphere, and it obscures the surface so completely that for decades, scientists could only guess at what lay beneath. What they could see was the atmosphere itself, and it was immediately striking. Titan is the only moon in the solar system with a substantial atmosphere, not a thin, barely there envelope of gas like the Moon or Mercury, but a genuine layered, complex atmosphere denser than Earth's, 1.5 times the surface pressure of our own planet. From space, Titan looks less like a barren rock and more like a small, hazy planet, something alive with process, something that has weather. That impression, it turns out, is not entirely wrong. When the Cassini spacecraft began making detailed observations of Titan in the mid-2000s, and when the Huygens probe descended through its atmosphere in January 2005 and returned the first images from the surface, what scientists found rewrote everything they thought they understood about where complex planetary processes could occur. Titan has a complete liquid cycle. Methane evaporates from the surface, rises into the atmosphere, forms clouds, falls as rain, and flows across the landscape in rivers and streams that drain into lakes and seas. It is the same process as the water cycle on Earth: evaporation, condensation, precipitation, collection, running on a completely different chemical at a completely different temperature on a world 1.2 billion kilometers from the Sun. The seas are real. The Ligeia Mare, one of Titan's largest methane seas, covers an area comparable to the Caspian Sea on Earth. The Kraken Mare, Titan's largest body of liquid, is larger than the entire Caspian Sea and Black Sea combined. These are not shallow puddles or thin films of frost. They are deep, open bodies of liquid, kilometers across, sitting under an orange sky at a temperature of -179 degrees Celsius. But something even stranger happens on the surface of those seas. Titan's methane oceans behave differently from water. Liquid methane is far less viscous, thinner, lighter, more responsive to disturbance. The waves on Titan seas are estimated to be small, just centimeters in height under normal conditions, because the lower gravity and different fluid properties produce a calmer surface than Earth's oceans. But during Titan seasons, which last roughly 7 Earth years each, conditions change. Methane storms roll across the surface. The seas churn. Hydrocarbon rain hammers the landscape in storms that, while brief, reshape the terrain below. Tides rise and fall on Titan's seas, driven not by a moon, but by Saturn itself, the enormous gravitational pull of the ring giant tugging at Titan's liquid surface from 1.2 million kilometers away. The tidal forces are weak by Earth standards, but they are real, measurable, and they mean that Titan's oceans are not static. They move, they breathe, they respond to forces operating across distances that dwarf anything in our own experience. Imagine descending through Titan's atmosphere. The first thing you notice is the color, a deep, burnt orange glow that pervades everything, the result of complex organic molecules called tholins coating the haze particles in the upper atmosphere. The sun from this distance is just a faint bright point in the haze, 100 times dimmer than it appears from Earth. It is not dark exactly, but it is nothing like daylight. The atmosphere is thick and calm. You fall slowly. Titan's lower gravity and dense air mean that descent feels almost gentle compared to entering Earth's atmosphere. Around you, hydrocarbon clouds drift in slow formations, made of methane droplets condensing in the cold. Occasionally, one of those clouds releases its contents as rain, not a light drizzle, but slow, heavy drops of liquid methane falling through the cold air, each one evaporating partially before it lands, leaving the surface wet and dark. And then the surface comes into view. It is not what you would expect. Near the equatorial regions, vast dunes stretch across the landscape. Not sand dunes, but dunes made of hydrocarbon particles, dark and fine, piled into ridges by Titan's sluggish winds. They resemble the great sand seas of the Sahara in shape, but their material is organic, complex, the chemical residue of billions of years of atmospheric chemistry raining down from above. Further toward the poles, the dunes give way to river channels, dark branching lines cut into the icy surface by flowing methane, carved over geological time into networks that look, from above, almost exactly like river systems on Earth. Follow them far enough and they lead to the methane seas, flat, dark, still under the orange sky, their shores lined with the same hydrocarbon material that covers everything else. Icy mountains rise in places, made not of rock, but of water ice, as hard as granite at these temperatures, pushed up by ancient geological forces. It is the most Earth-like landscape in the solar system, and it is completely, utterly alien. But the surface is not the deepest secret Titan holds. Beneath Titan's icy crust, beneath the methane seas and the hydrocarbon dunes and the frozen river channels, there is strong evidence for something extraordinary. Data from the Cassini mission detected subtle variations in Titan's rotation and gravitational field that are most easily explained by the presence of a subsurface ocean of liquid water, sandwiched between the icy crust above and a rocky core below. Liquid water, deep underground, possibly in contact with rock, possibly warm enough near the core to sustain chemical reactions of the kind that, on Earth, support entire ecosystems of life in the deep ocean with no sunlight at all. Titan may not have one ocean, it may have two, one of methane on the surface, one of water beneath the ice, and either of them, scientists argue, could potentially harbor life. On Cosmic Vision, we explore worlds that force us to rethink what we mean by the word possible, and Titan forces that rethink harder than almost anywhere else. The surface chemistry of Titan is extraordinary. The atmosphere is continuously producing complex organic molecules, carbon-based compounds of the kind that, on early Earth, are thought to have been the building blocks of life. These molecules rain down onto the surface and accumulate in the dunes, the lake shores, the riverbeds. Titan's surface is, in a very real sense, coated in prebiotic chemistry, the raw ingredients that preceded life, preserved in deep freeze on a world that has been accumulating them for billions of years. Could something live in Titan's methane seas? Not life as we know it. Not life built on liquid water, oxygen, and carbon chemistry operating at room temperature. But theorists have proposed the possibility of a completely alien biochemistry, life that uses liquid methane as its solvent instead of water, that metabolizes acetylene instead of sugar, that breathes hydrogen instead of oxygen. Such life would be so different from anything on Earth that we might not recognize it, even if we found it. The temperature alone would make it unlike anything in our experience, minus 179 degrees Celsius. But life on Earth has repeatedly demonstrated that the boundaries we draw around its possible habitats are almost always wrong. The Cassini-Huygens mission transformed our understanding of Titan more than any other. Cassini spent 13 years orbiting Saturn and made over 120 close flybys of Titan, mapping its surface through radar, studying its atmosphere, watching its seasons change. Huygens descended through the atmosphere on January 14, 2005, and in the 2 hours and 27 minutes it took to reach the surface, transmitted more data about Titan than all previous observations combined. But the next mission may go further still. NASA's Dragonfly, a rotorcraft lander approved for launch in the late 2020s, is designed to fly through Titan's atmosphere under its own power, hopping between locations across the surface, sampling the chemistry of the dunes and the river channels and the terrain near impact craters where subsurface material has been brought to the surface. It is the most ambitious moon mission ever attempted, and its primary scientific objective is to determine whether Titan's chemistry has taken any steps toward the origin of life. The answer, whatever it is, will be one of the most significant scientific findings in human history. Titan sits quietly in Saturn's orbit, wrapped in its orange haze, its methane seas flat and dark beneath a sky the sun barely reaches. From a distance, it looks almost peaceful, a soft, glowing world drifting in the cold of the outer solar system, unhurried and still. But beneath that stillness is a world of extraordinary complexity, a world with weather and seasons and oceans and rivers, a world whose surface is coated in the chemistry of life's origins, a world that may hide a liquid ocean beneath its ice, and may harbor life forms so different from our own that the word itself barely applies. We have touched it once, briefly, imperfectly, through a probe that lasted less than 3 hours on its surface before going silent. We are going back, and when we do, the questions we bring with us are the oldest questions of all. Are we alone? And if not, does life out there look anything like us? Titan may not give us the answer, but of all the worlds in this solar system, it is the one most likely to bring us closest to asking it in the right place.